Gas stoichiometry is where we're moving next. I've got 3 examples that I want to go through with you guys, and I don't want to take up a ton of your time, so we're going to get right to it. So again, as has been the standard, black is what would be given to you in the question. Blue here is what you would write down on the page or information that you could glean from either your data booklet or whatever. Again, first, we've got our chemical equation that's basically described up in the problem up above, and I've written my balanced chemical equation here. So step number 1 to stoichiometry is write a balanced chemical equation. Then, given my information in the problem, I've organized the information that I've got here down below, just like I've done before. So I've got my mass of sodium azide, which is 130 grams, my molar mass of that, because if I'm given a mass, I definitely want a molar mass for that. And then the question tells me, it wants me to calculate the volume of nitrogen that's produced if that much sodium azide decomposes. And so the volume is what I'm looking for. That's my required. This is my given. And then it tells me that this is all happening at SATP. And if you remember, that was a condition that we talked about in the gas unit, which is standard ambient temperature and pressure. And so there's some standard conditions that exist that you need to know where to find them. They're in your data booklet. But SATP is 100 kilopascals for pressure, and the temperature is 298 Kelvin, or 25 degrees Celsius. So I've written those numbers down here. I've written my temperature in Kelvin because the formula that we're going to end up using is the ideal gas law formula, this PV equals nRT. And the temperature parameter for this formula has to be in units of Kelvin. So I go ahead and I do step number 2. Step number 2 in stoichiometry is simply calculate the moles of the given. And this is really no different here than what we did in gravimetric stoichiometry, where we've got a mass. We use the molar mass to calculate the moles. That's step number 2. Step number 3, convert the moles of the given into the moles of the required using the mole ratio. And so there's step number 3. Now where things get a little bit different is not that step number 4 has changed. Step number 4 is calculate what the question is asking for. And so in this step here, I am going to calculate what the volume of nitrogen gas is, but I have to use the information now that I have made up to this point to do that calculation. And because I don't have because I'm not being asked to calculate a mass here, I don't need the molar mass. I'm not going to use the molar mass. And so to calculate volume, because this is a gas, I'm going to use the ideal gas law, PV equals nRT. And you can see in this formula, I have a variable that denotes or calculates volume. And so if I rearrange that formula so that I can calculate volume, my formula would look like this. V is equal to nRT divided by P. And so you can see that I've plugged in the numbers that I've been given in the question to do that calculation. So here is 3 moles of nitrogen gas. This is after step 3, I have the moles of the required. My required is nitrogen gas, so 3 moles goes into that spot for N. R is just the ideal gas law constant that's found in your data booklet. It's 8.314, so I plugged that in there. The temperature is given to me in the question as part of SATP. So 298 Kelvin goes there as per the formula. And then on the bottom, the pressure number is 100 kilopascals, and so I plug that in. I punch this into my calculator. Remember, this number here is going to be a big long number in your calculator. Don't round until the end, so you need to use the big long number in your calculator, not the rounded 3.00. And when you do that and you plug that all in, you're going to get 74.3 liters. Now for this particular problem, it actually turns out that this last step can be done in a slightly different way if you would like. This is only doable though for problems where they tell you the conditions are at STP or SATP. For this one, it says it's at SATP, which means that not only do I have 100 kilopascals and 298 Kelvin, but I also know what the molar volume is of ideal gases at those conditions. And the molar volume is 24.8 liters per mole at SATP. And so I can just take these 3 moles of N2, use the molar volume of N2, which is going to be 24.8 liters per mole because it's at SATP, and I can cancel out my moles and I can get my liters, and you can see that the answer is exactly the same, punches out in your calculator as 74.3 liters. So there's two different ways that you can choose to do it. Now, if you have a problem where it gives you a specific pressure and a specific temperature, it doesn't say it's at STP or SATP, then you are not allowed to use this step down here. You're only allowed to use the molar volume of SATP if the question tells you that the conditions are at SATP. And so that's it. That's example number one. I'll be right back with the next one. It's example number two here up on the board. We've got our balanced chemical equation. Again, running through the steps of stoichiometry. Follow along with me. Step number one, write a balanced chemical equation. So here it is. I've got the decomposition of sulfur trioxide, and that decomposes into S8 and O2. Remember that if I'm decomposing this into its parts, sulfur and oxygen, remember that sulfur is a polyatomic element, and so it is S8 when it's by itself, and oxygen is O2 when it's by itself. If you don't remember that, that's going to affect your balancing of these chemical equations and get you the wrong mole ratio when you get to step number three, and which will then get you the wrong answer. So you got to make sure that you're careful about that. So there's my balanced chemical equation. You can see that I've organized my information again as per we've always done. So again, it says what mass of sulfur will form. So that's my required. It gives me some information for sulfur trioxide. So I've written that information down here. Notice that the temperature that I've written down is in Kelvin again. And then because I'm asked for a mass here, I need my molar mass right below it, because I'm going to need to use that in order to calculate my mass at that point. And then at this point, this is where maybe it kind of gets a little tricky for some. Ultimately, what you just need to remember is that if you have a gas substance or a substance in the gas state that they give you a volume, a pressure, and a temperature for, then you're going to be using the ideal gas law in some form. But remember, step two is calculate the moles of the given. So unlike the previous example when we used this formula to calculate for volume, here in this step, I need to use that formula to calculate for the moles of SO3. So I'm going to rearrange the formula so that I can solve for moles here. PV, divide by RT. A real common mistake that a lot of kids will make is that they'll try and rearrange this in their head, and they will erroneously make this N is equal to RT divided by PV, which is backwards. It's not the way that you rearrange that formula. So make sure that you're rearranging this formula correctly. PV over RT is how that's going to be. Then I just plug in my numbers that I'm given here. You can see my pressure goes in, my volume goes in, my R is just the ideal gas law constant. That's in the data booklet again, 8.314 goes on the bottom. And my temperature goes in as Kelvin, not degrees Celsius. I plug this into my calculator and I get 1.22 moles of SO3. That's step number two, moles of the given. Then step number three, calculate the moles of the required, or convert the moles of the given into the moles of the required using the mole ratio. So 1 mole divided by 8 moles. And then step number four, calculate what the question is asking for. Here I'm asked for mass, so I'm going to use the molar mass to convert the moles into mass. And there's my answer, 39.0. You can check my math if you'd like. One thing I want to make sure that you're doing on a regular basis is that you are analyzing your units to make sure that your units match out and punch out the way that they should. If you're getting grams on the bottom of the fraction, and that's the way you've analyzed your units, you've done something wrong there. You've put numbers in the wrong places or units in the wrong places. You've got to go back and find the error. So if I take a look at this, I've got kilopascals on the top and the bottom, liters on the top and the bottom, Kelvin on the top of the bottom and the bottom of the bottom, which allow them to cancel, and I'm left with moles here. So I've got moles, and then these moles cancel out, these moles cancel with these moles, and then those moles cancel there with that, and I'm left with, this is 1.22 moles of SO3, so that SO3 will cancel, you know, I've just kind of left that one out there. And then grams of S8 is what I'm left over with, 39.0 grams of S8. I'm pretty confident that that's the right answer. So that's example number two, back with one more. All right, guys, so here is our final example as it relates to gas stoichiometry. And so you can see I've got my balanced reaction up here, and I've established what my required is and what my given is right there. And I've written my numbers down below that correspond to that. Now, something I want to point out, again, these numbers come from the fact that we're doing STP here. So STP is nice because we've got the pressure and the temperature, but we also have the molar volume if you want to select to do it that way. But the first two examples that I went through with you guys, the first one, it gave us a mass for the given, and we had to calculate a volume. The second example gave us a volume, and we had to calculate the mass. So you can see how those are kind of reversed. In this one, this example is, it gives us a volume, and it's asking for us to calculate a volume. And so what I want to show you here is this question can actually, this seems like a lot of work. This question is actually the easiest kind to do. And so let me illustrate to you how this works and what all is kind of happening here. So the first way I can look at this is I can just do the stoichiometry, right? So I did step number 1, balanced equation. Step number 2, calculate the moles of the given. So I've done that using this formula here. N is equal to PV divided by RT. I plug in my numbers, my P's and R's and T's and V's and everything, and I get a certain number of moles of N2. Then I convert that into the moles that are required by using the mole ratio. There it is, step number 3. And then step number 4 is calculate what I'm looking for. Again, what am I looking for? Volume. V is equal to nRT divided by P is what I'm going to use here. Plug that in. This number here that I get at this point is a certain number of moles. I'm going to multiply that number by R and T divided by P. So that's why the N isn't really written in here. It's because it's assumed that that is being used in the calculation. So whenever I hit equal at this point, I'm just going to hit times and then times it by R and T. Then divide it by the pressure. And I end up with 50 liters. But take a look at the unit analysis here. If I take a look at this, I can see, look at this is multiplication all the way across. So I can look and cancel things out. Not only can I cancel kilopascals, but I am timesing by 101.325 kilopascals over here and dividing by 101.325 kilopascals over there. Those can cancel, that just equals 1. I am multiplying by 8.314 and dividing by 8.314. And also, I'm dividing by 273 and multiplying by 273. So all that's left here in the calculation is 25 liters times by 2 divided by 1. In other words, just the mole ratio. And if you remember from the gas unit, this is what was referred to as the combined, not the combined gas law. This was referred to as the law of combining volumes, where if I have a chemical reaction where I've got a gas being converted into another gas, I can just use the mole ratio here to convert the volumes into what those are. So you can see that I've got a 2-to-1 ratio here for volumes, or for moles, for amounts. And because ideal gases or gases are considered to be ideal, that they all occupy the same amount of space at the same pressure and temperature, then the volume is only going to change by that same ratio as well. So if this is 25 liters here, then this is going to be 50 liters here. And so it makes the question a lot more simple. Again, if you were given STP conditions, you could do the same thing down here below, and you can see the same thing rings true. Moles cancel, 22.4 liters on the bottom, 22.4 liters on the top, moles on the top, moles on the bottom, and all I'm left with here is 25 times by 2 gives me 50. So both methods work, and this is just a law of combining volumes type of question. So that's what you need to know, guys, for gas stoichiometry. You can jump into the practice. Thanks for watching.